Chapter 6. Now, before we get into Chapter 6 topics, I just want to remind you, probability was introduced into Chapter 4. Chapter 5, we looked at probability distributions as well as binomial probability distributions. Well, in Chapter 6, we're going to continue talking about probability distributions. But now we're going to confine our discussion to what is called a normal probability distribution. So we first have to know what that is. So what we're going to do first is we're going to review all the different distribution shapes. So when we created histograms back in Chapter 2, we talked about all the different distribution shapes. So I'm just going to give rough drafts of some of those. We had symmetrical, we had uniform, we had skewed left, skewed right, and then the last one was bimodal. Now, if you recall, each bar represents a frequency. The height of the bar was because of the frequency of the number of data values that would fall within that class. So to figure out one of these 5 is what is called the normal distribution. So if we were to connect the tops of the bars, that one's odd. It helps, gives us a visual when we look at these to say, okay, what might be considered normal? And hopefully your eye is drawn to symmetrical. So Chapter 6, we will be confining our discussion to only normal distributions or symmetrical bar graphs. The others are not what we're talking about in Chapter 6. The normal distribution is one of the most important examples of a continuous probability distribution. Continuous, remember when we had random variables, they were discrete or continuous. So the normal distribution is one of the most important examples of the continuous probability distribution. A normal distribution graph is called a normal curve or and what does this shape kind of look like? They call a bell-shaped curve. Now, there are some specific characteristics that go with a normal probability distribution, and that's what we're going to look at next. So the characteristics of a normal curve. Okay, I'm going to draw a normal curve down here. All right, so first, bell-shaped, so I have my bell, with the highest point over mu. So the tallest point, this is mu. It is symmetrical. What that means is the same amount, if I were to fold this in half, it would look the same on both sides. So if this is the complete curve, then here to the right of mu is half of my curve, and to the left of mu is half of my curve. The curve approaches the horizontal axis but never touches or crosses it. So here's my horizontal axis, this whole thing across here, and it's saying as this curve, what it does is it approaches it and it gets closer, but it would never touch nor would it cross this on this side or this side. We have what are called inflection points between cupping upward and downward, and those occur above mu plus 1 standard deviation and mu minus 1 standard deviation. So it'd be about, my picture may not be exact, but this right here, these are considered your inflection points. And this is mu plus 1 standard deviation, mu minus 1 standard deviation. The area beneath the curve and above the axis, so if I were to shade in, it's talking about all of this. So this area is 1 or 100%. Area and probability are in essence the same thing. One thing that you'll notice is when we work or we calculate areas, my answer is given as a percent. Probability, if it asks for probability, I give my answer as a decimal. Now, here is a picture that shows two different normal curves. You'll see the dotted line and then the solid line. They're both normal curves, but this solid line goes up higher, and then the dotted line is shorter and goes out further to the left and the right. Well, the difference in that, if you look up here, the solid line has a mean of 52. The dotted line also has a mean of 52, so their average is the same, but the big difference is the standard deviation. So the solid line has a smaller standard deviation, so it's taller and skinnier. The dotted line is shorter and fatter, but under each curve is still 100% of the area or the probability. All right, we are asked to sketch a normal curve with mu of 2 and sigma of 5. All right, so I'm going to draw a normal curve. Now, when we're dealing with a normal curve, we know that the tallest, or what cuts it in half, is mu, and they tell me that mu is 2. And then what we always do, here's my first inflection point, but we go out 3 standard deviations. So to the right, I went out 1, 2, 3 standard deviations, and I'm going to do the same thing to the left. So I start at mu of 2, and my standard deviation is 5. So as I go to the right, I add 5. So 2 plus 5 is 7, plus 5 is 12, plus 5 is 17. And as we go to the left, we would subtract 5. So 2 minus 5 is negative 3, minus 5 is negative 8, minus 5 is negative 13. Now, this complete curve has an area of 100%, or a probability of 1. Well, when we're talking about symmetrical, that means from mu to 1 standard deviation that the area or the probability in this bar is exactly the same in this bar. Now my picture doesn't look that way, but it is symmetrical. So this amount is 34% or 0.34, which means here we have 34% or 0.34. Between the first and second standard deviation, it is 13.5% or 0.135. Between the second and third standard deviation, it is 2.35% or 0.0235. And then, of course, we have our tails. And if I were to add all of these up to figure out my tails, I have 2 34% plus 2 13.5% plus 2 2.35%, and that gives me 99.7. So I'm going to do 100 minus 99.7. So my two tails are 0.3, and if it's symmetrical, I'll divide that by 2, so it's 0.15%. So my tail is 0.15% or 0.0015. Now, these percentages right here, this is a normal curve. As long as the problem states that it is a normal curve, these percentages hold true all of the time. This 34% will always be 34%. These percentages do not change as long as you know it's a normal or symmetrical curve. Now, we have what is called the empirical rule. And again, this is only true for a normal distribution. This does not hold true for uniform, skewed, or bimodal. Only a normal distribution. And that tells me that approximately 68% of the data falls within one standard deviation. So I look up here, here's one standard deviation. So it's telling me that 68% of the data would fall between -3 and 7. Approximately 95% of the data fall within 2 standard deviations. And of course, if you would add 13.5 plus 34 plus 34 plus 13.5, you would get 95%. Sorry, there we go. That's where they get the 95. They add those all together. And then lastly, approximately 99.7% of the data falls within 3 standard deviations. Pull this all the way down. I don't think the first time I did. And then, of course, then that leaves our tails. So each tail or each end of the normal curve contains approximately 0.15% of the data values. So this curve right here, all of these percentages, because remember, here this is mu plus 1 standard deviation, mu plus 2 standard deviations, mu plus 3 standard deviations. And to the left, we have mu minus 1 standard deviation, mu minus 2 standard deviations, mu minus 3 standard deviations. So as long as we have a normal curve, we will always apply these values. And that's what we are going to look at next. So keep this handy because we're going to use these numbers. Use the empirical rule to answer the questions. It wants us to draw the curve, shade and calculate how much of the area probability, remember area we give our answer as a percentage, probability is a decimal, under the curve between the vertical lines. All right, I'm going to do this where we can get a little bit closer. So my vertical lines are going to be at mu and mu plus 1 standard deviation. So I'm going to draw my curve, and I have a normal curve. I know mu is right in the middle, and I'm going to go to 1 standard deviation. I am going to shade, and it wants to know how much of the area is shaded. So I'm going to go back here between mu and 1 standard deviation, that is 34%. So area would equal 34%. If I gave my answer as a probability, it would be 0.34. All right, this second one. Draw my curve. And now I have mu and mu minus 1 standard deviation. Shade. So now it's the same bar, it's just on the opposite side. Well, since this is symmetrical, then we know that that is 34% as well. Whereas a probability, 0.34. My vertical lines are at mu and 2 standard deviations plus, so I'm going to the right. So that means I need to add, if I go back to this, it's adding this and this. So for area, it would be 34% plus 13.5%, which gives us 47.5%. And as a probability, you would just write that as a decimal. We have mu minus 1, minus 2, minus 3 standard deviations. Now, in this one, I always ask students if they see a different way in which to find the area that is shaded. Now, based upon what we've done, students typically just do addition. 34% plus 13.5% plus 2.35%, which gives us 49.85%. And that's correct. You would get full credit, you would have done it correctly. But I always also ask my students, do you see another way in which you could have gotten the same correct answer? Well, one way is, if you'll notice, the left half is completely shaded in except for this tail. So one way we could have found the same answer is to take 50% and take away the part that is not shaded, which is 0.15%. And that would give you your 49.85% as well. The other, I have students recognize that this is shaded to the left 1, 2, 3 standard deviations. Well, the empirical rule tells us that 99.7% is within 3 standard deviations. So I will have some students that say, well, how about 99.7%, but that would be 3 standard deviations to the left and to the right, and then just take half of that or divide it by 2 to give you your 49.85% as well. all of those are correct. Whichever way you see it is the way I would do it. And then, of course, as a probability, that would be 0.4985. Now, all of the examples that we have done so far, mu has been one of our vertical lines. That will not always be the case. Now, I'm going to go ahead and draw mu, but it's not going to be what I shade to, but I just do that so I can cut my normal curve in half. But this says go -1 standard deviation and +2. So if you'll notice, we have 2 of them that are 34%, or using the empirical rule, it says within 1 standard deviation is 68%, so you might have recognized that right off the bat, plus this 13.5%, which gives us 81.5%, or as a probability 0.815. And then the last example on this page, mu +1 standard deviation and mu +3 . So to find the area, we did not include the 34, but we have the 13.5% and we have the 2.35%, which is 15.85%, or as a probability, 0.1585. So here we just did several examples of how to find the area or probability located under a normal curve. Because again, remember, these numbers hold true for all normal curves. So now let's apply that to some additional problems that make us apply the information that we just learned. The yearly wheat yield per acre on a particular farm is normally distributed with a mean of 35 bushels and a standard deviation of 8. So this is what you want to look for right here. When it says it's normally distributed, then you know you can use those percentages. So the first part A says draw the curve and shade the area under the curve that represents the probability that an acre will yield between 19 and 35 bushels. All right, so I'm going to draw a curve. Now, for this curve, they told us that mu is 35, so that tells me that cuts it in half is 35, and sigma, or the standard deviation, is 8. So as I go to the right, I will add 8. So 35 plus 8, 43, plus 8, 51, plus 8, 59. And as we go to the left, we will subtract 8. So 35 minus 8, 27, minus 8, 19, minus 8, about put negative, sorry about that, that should be 11. Disregard that little dot right there. So there's the curve. And it wants us to shade the area between 19 and 35. So here's the 19, here's the 35, so it wants me to shade this area right here. All right, so that's part A. B says, is the area the same as the area between mu minus 2 sigma and mu? Well, we know that in the middle is mu. Here we have mu plus 1 standard deviation, plus 2 standard deviation, plus 3 standard deviation. And as we go to the left, minus 1, minus 2 standard deviation, minus 3 standard deviation. So is it the same between mu and minus 2? And sure enough, yes it is. Use the drawing to find the percentage. So percentage, we're dealing with area over the interval between 19 and 35. So it wants to know these percentages. Well, we know this is 34% and this is 13.5%. So to find the area, we're going to add those two. So we get 47.5%, and it asked for the percentage of the area. Then part D, what is the probability? So now it's asking me to find the probability of that same between 19 and 35. So it's this same answer, it's just written differently, because the probability that it's between 19 and 35, and now I'm going to change that to a decimal. So that's what it would look like written as a probability. The amount of coffee dispensed by a coffee vending machine, normally distributed, with a mean of 7.6 ounces, and a standard deviation of 0.4. So it first asked me to draw the distribution. Well, they gave me that mu is 7.6 ounces and sigma is 0.4. So I'm going to draw a curve. So mu is 7.6. And then as we go to the right, we will add 0.4. So this would be 8 or 8.0 ounces, 8.4 ounces, 8.8 ounces. And then as we go to the left, we will, sorry, my curve's a little crooked, we'll subtract 0.4. So this would be 7.2 ounces, 6.8 ounces, 6.4 ounces. Now, the first question asks, find the probability that it will overflow an 8-ounce cup. Well, here's 8 ounces. Anything in the cup, if my cup is 8 ounces, anything here to the left, it will stay in the cup. But the overflow would be this. So that overflow, now it's probability, so I'm going to write these as decimals. So this is 0.34, this is 13.5% or 0.135, 2.35% or 0.0235, and then a lot of students forget or they neglect to include the tail. So don't forget the tail because the overflow also includes the tail. So that would be 0.0015. So we add all of those together and we get, whoops, 0.16. All right. Next question. Well, I like my 0 in front of it. Okay, there we go. Part C says, find the probability that it won't overflow an 8-ounce cup. Well, won't overflow is the non-shaded portion. Well, what is the relationship between the shaded and the non-shaded? Well, these two would be complements. Getting ready to sneeze, so excuse me. And we know complements have to add up to 1, so I could just do 1 minus 0.16 or 0.84. Overflows, makes a mess, doesn't overflow. So the last question is going to have you take your probabilities and apply it to a real life situation. So if we have 850 cups, how many do you expect to overflow? Well, I expect 0.16 or 16% of the time for them to overflow. So I would just take 850 times 0.16 because I want to know 16% of 850, and that equals 136. So I expect 136 of the cups to overflow, which seems kind of high. All right, last example in this section. Assume normal distribution, and we have that Doug scored a 57 on the Miller analogies test, which has a mean of 50 and a standard deviation of 5. Jennifer scored a 120 on the whisk test, which has a mean of 100 and a standard deviation of 15. Compare their scores. Who had a better score? All right, so Doug took the Miller analogies test. He scored, so his X value is a 57. It has a mean of 50 and a standard deviation of 5. So what would Doug's score look like on a normal curve? So the mean is 50, and as I go to the right, 3 standard deviations, I add the standard deviation of 5, so this would be 55, 60, 65. As I go to the left, I would subtract 5, so 45, 40, 35. And I'm going to locate Doug's 57. Well, here's average. Anything to the right is above average, so I know Doug scored above average. He scored a 57, which would be between 1 and 2 standard deviations. So it would be approximately right here. His score 57. So we want to compare that. So now I need to draw Jennifer's over here. And she took the whisk. Now, she scored a 120. Now, if they took the same test and I could compare the 120 to the 57, well, I'd say Jennifer blew him out of the water. But they took 2 different tests, 2 different means, 2 different standard deviations. So we can't do that. For her test, the mean is 100 and the standard deviation is 15. So now I'm going to draw a normal curve and locate Jennifer's score. So the mean is 100. To the right I'll add 15. So 115, 130, 145. And as I go to the left, I will subtract 15. So 85, 70, 55. Now, here's average. So if Doug had scored 50 and Jennifer had scored 100, they both would have scored the same on the test. If Doug would have scored a 55 and Jennifer would have scored a 115 on her test, they would have scored the same. So Doug is above average. So if Jennifer's below average, I know Doug did better. Well, Jennifer is above average. Well, Doug is between 1 and 2 standard deviations. So if Jennifer is anywhere to the left of 1 standard deviation, then I know Doug did better. Well, she's at 120, which would be approximately right here. So now I look at this and go, they both scored above average. They both scored between 1 and 2 standard deviations. And within those, between 1 and 2 standard deviations, it appears that they scored exactly the same. Now, that completes this example. When we do 6.2, we will come back to this and look at how to directly compare, because right now it's too hard. But that completes 6.1.